This is the first theoretical lecture of the week that starts in the 17th of May, and this lecture is related with particular cases and scheduling problems. So we are going to divide this lecture in two parts. In the first part, we are going to look to particular cases, that is, transportation problems and allocation problems. And in the second part, we are going to look to scheduling problems. In both cases, we are going to use as case studies problems of our list of problems. That is problem 11, problem 12, and problem 14. So let's start with the transportation problems. To illustrate this kind of problems, we are going to use problem 11 of our notes. In this problem, we have a situation in which a company buys from 4 laboratories boxes of medicine products that are delivered to 5 clients or customers. So we have here information related with the planning of the transportation for a given week, and we have information about the demand that the customers require. Customer 1 wants 20 boxes, customer 2 27, and so on until customer 5, which requires 6 boxes. We have also information about the availability of boxes from each supplier. Supplier 1 can provide 20 boxes and so on until supplier 4, which can provide 5 boxes. And in the table, we have information about the cost of transporting 1 box from a given supplier to a given client. And our objective is to formulate the linear programming problem so that we can optimize the ordering and the distribution plan so as to minimize the transportation costs. Now, to formulate the problem, we need to start by identifying the objective. And of course, that we already stated that and it corresponds to minimize the total transportation cost. Then we need to identify the decision variables. Well, we also already illustrated that we want to define the quantity that should be transported from supplier or laboratory I to customer CJ. And in terms of the restrictions, we have 2 kinds of restrictions. One related with demand. So demand must be satisfied. That is, the clients must receive what they asked. And another kind is related with the supply. And the laboratories, they cannot supply more than what they have available. Well, we have also information present in the table in which we are going to define these coefficients. So the cost of transporting 1 box from 1 laboratory to a given client is denoted by Cij. The availability from suppliers is denoted by Ei, and the quantity ordered by a given customer is denoted by Bj. So before starting writing the linear programming problem, we must verify first if there is a balance between supply and demand. From the supply side, we have 60 boxes available, but from the demand side, we require 65 boxes. So we cannot satisfy, in this case, the demand with this availability. And of course, mathematically, this problem has no solution as it is. So we need to create a fictitious laboratory, which we are going to label L5, that will provide 5 fictitious boxes so that supply and demand is equilibrated. Of course, that the transportation costs of delivering these fictitious boxes is 0. Before starting writing the problem, we must identify all variables in a matrix like we show here. This helps us to identify, for example, if we consider a line in this matrix, for example, the first line, if we add the variables that are in this line, we get what supplier 1 will provide. And if we add, for example, the variables that are in the first column, what we get is what client 1 will receive. So in this way, it's easy to write not only the objective function, but also the restrictions. So in terms of the objective function, we have also here the table with the costs of transporting one box from one supplier to one client. And the objective function is just this product that involves the elements of these two matrices. Of course, that we don't need to consider the last line, because the last line of variables is related with the fictitious quantities. So we start by multiplying 300 by x11, then we have 350 that multiplies x12, and so on until we arrive here to 200 that will multiply x for 5. So this is the objective function. So now we have the restrictions, and we have two kinds, those related with the supply side, and in the supply side we just can state that the supply that will be provided cannot exceed what is available. So we saw previously that the variables in a line of the matrix of the decision variables corresponds to what is supplied by a given supplier. So we just need to consider the lines of that matrix and the availability of each supplier. So first supplier can provide up to 20, second one 15, until the fictitious one that can provide 5. So these are the restrictions related with the supply side. So the elements in a column of the matrix of decision variables is related with the quantity that the customers will receive. So the customers, they must receive at least what they require. So the first customer requires 20 boxes, and the variables that we have here, of course, are the ones that are in the first column of the matrix of decision variables, and so on. So we have for the second customer 17 until last customer that requires 6 boxes. So we can solve the problem using software like Lind, for example, and then we can analyze the solution. So we have here the solution for the decision variables, which are present in the matrix, and we can then verify that in fact each supplier provides what they have available, and each client receives what they require. Nevertheless, client 3 receives 8 units, but 4 of them are fictitious. So in fact, this client will not receive all the boxes that asked, and the same for client 5. So he receives 6 boxes. Nevertheless, one of the boxes is a fictitious one. So in practice, it receives 1 box less. So let's illustrate the allocation problems, and we are going to use as an example problem 12 of our list. In this problem, we want to recruit 4 engineers to perform different functions, but we have 5 candidates. So one of the candidates must be excluded. These candidates, they were evaluated, and we have their performance for each or their ability for each of the positions. For example, candidate 3 has a score of 6 for place 1, but a score of 9 for place 3, and a score of 3 for place 4. We have here a problem that is similar to the transportation one. That is, each candidate is available for 1 place only, and each place requires only 1 candidate. Of course, that we want to formulate the linear programming problem that allow us to decide the allocation of the four of the candidates, and of course to decide which one must be excluded. So to formulate the problem, we must begin by identifying the objective. In this case, is to maximize the total benefit of assigning workers to the tasks. The decision variables xij will indicate whether worker I is allocated to task j or not, but these variables are binary, that is, they receive the value 1 or 0, 1 if yes and 0 if not. And then the restrictions. As in the transportation problem, we have to deal with the supply side and with the demand side. In the supply side, we must ensure that each worker can only be allocated to one job. In the demand side, each job will receive only one worker. And of course, this problem must also be balanced. So supply and demand must be equal. This means that we need one fictitious post. We have 5 candidates, we need 5 posts. So the fictitious post, of course, each candidate, the suitability of each candidate for this position is of course 0. So we start writing the problem considering the objective function. So the objective function is the total ability which is obtained multiplying the ability of each candidate for each position by the allocation of each candidate, and of course we want to maximize this total ability. So for example, we can illustrate here the calculation. So we have the ability of the first candidate for the first place, which is 5, must be multiplied by the allocation of this candidate to this place. So we have 5x11. Then for place 2, 6x12, 6x12, until the last candidate to the last position, x54, which is multiplied by 7. Of course, that we don't need to consider the allocation in the objective function for the fictitious position, because the ability to each candidate to these positions is 0. Let's consider now the restrictions, and let's start with the candidates. So each candidate can be allocated once. So adding the variables in the decision matrix lines, we obtain the assignment of each candidate. So, and each candidate can be assigned only once. So for each candidate, we have a similar relation, which is obtained simply by adding the lines of the decision matrix and assigning the result, the value 1. So in terms of the posts, each post will receive only one candidate, and what give us what is assigned or who is assigned to each post is the variables that are in the columns. So the first column of the matrix corresponds to the assignment of the first post. So this is what we have here. So this is the variables in the first column. So this is the assignment corresponding to first post, to the second one, and to the fictitious one. And we can obtain the solution of this problem using software like Lindo, and we already have here the solution. So we have here the values of the decision variables. So we can see here, for example, that candidate 4 is assigned to the first position, candidate 1 is assigned to the second post, candidate 3 is assigned to post 3, candidate 2 is assigned to post 4, and candidate 5 is assigned to the fictitious posts. That is, candidate 5 is the one that is excluded. And now let's look to an example of a scheduling problem. That is problem 14 of our list. So in this problem, we have a supermarket with the different needs of employees during each day of the week, as we represent in this table. That is, on Monday they need 17, on Tuesday 13, and so on. We know that each employee works 5 consecutive days, and it has to rest the following 2 days. Of course, we want to use linear programming problem to formulate the problem that allow us to minimize the number of people in this team. Now let's look to the formulation of the problem. We already know what is the objective. The objective is simply minimize the number of people in the team. Nevertheless, we need to define the decision variables so that we can translate this objective mathematically. And we can think in what will happen in practice. So in practice, we will have to divide the team in groups, the groups according to the days of the week in which they will rest, because they cannot rest all at the same time. So this is the same as classifying the groups according to the first day of the week in which they start working. So this is how we define the decision variables. Xi is the number of employees we will start work on day I of the week, in which the index I goes from 1 to 7 or from Monday to Sunday. So in this way, we can identify the number of people in our team as simply the number of people in each group. And now we need to establish the restrictions. So the restrictions, they must ensure that we have enough people working every day of the week. So we have here in the last line the requirements for each day of the week from Monday to Sunday. So what we list here is the groups that start to work in each day of the week. For example, group 1 starts working on Monday, and they will work until Friday, and then they will rest the other 2 days. Group 2 starts on Tuesday, and they will work 5 consecutive days, and then they rest the other 2 days. That is on Sunday and on Monday of the next week, and so on. So in this way, we now can evaluate the number of people that is working in each day of the week. For example, on Monday, what the number of people that will be working will be the number corresponding to the first group, that is X1, the number corresponding to the fourth group, that is X4, and through, of course, the last group, that is group 7. Okay, so and the requirements for this day is 17. So we just need to establish this relation, that is, the number of people working on Monday must be greater or equal than 17. And of course, we do the same for the other days of the week. So putting all together, we have our linear programming problem, which is an integer linear programming problem. It is an integer linear programming problem because the variables involved must be integer. So the objective function is the number of people working in the team, and the restrictions ensure that in each day of the week we have enough people to work according to the requirements. So we have one restriction for each day of the week, starting on Monday through Sunday. So we can solve this problem, but in this case we must specify that the variables are integer. So we use a different algorithm that is not the simplex method. So it's a proper algorithm for integer variables. So, and here we have the solution which we obtained with a software like Lindo, and we have this vector x that presents the number of people in each group, starting in those that start on Monday through those that start on Sunday. And now we can add them to see the dimension of the team, and now we can analyze the solution that building this table, in which we introduce here now the number of people in each group. For example, in group 1 we have those that start on Monday, we have 7 elements. In group 2 we have 3, so we introduce 3 from Tuesday to Saturday, and so on. So we include the number of elements of each group. We consider the days in which they rest, and then we go here in the columns to see how much people is working. For example, on Monday we have 19 working. Of course, that we cannot ensure that we will have exactly the number of people that is required, but we have at least those that are required. For example, on Monday we require at least 17, so we have an excess of 2 here on Monday. On Tuesday we have 1 more. Here there is exactly the number of people required. On Friday we have more 5 than necessary, and Saturday it's exactly, and on Sunday we have 2 more than necessary. Of course, that this is important for the decision manager, because now he can find extra work for them for these people that is not necessary to do. And this is it. This is the end of this problem, and this is also the end of this lecture. Thank you for your attention, and see you in the next one.